Okay, let's move on to part two. And the next problem we'll be working on is number 13. In number 13, we have a car that's on an incline. And the incline, all my cars, by the way, look like Honda Elements. And if you don't know what a Honda Element looks like, take a look at Mr. Hughes' car at times. When you have cars like this, the force diagram looks something like this. You have the weight, you have the normal force, which is perpendicular to the surface, and then you have what's called the parallel force. And by the way, you should remember this because we'll be talking about this some more in future chapters. So the weight is straight down, the parallel force is parallel to the incline, and the normal force is perpendicular. And as it turns out, this is 6% here. As it turns out, the angle right here is also 6%. And this obviously is a right angle. Therefore, Fn, the normal, is going to equal to the weight times the cosine of the angle. And Fp, or the parallel force, is equal to the weight times the sine of the angle. And this is what you need to know in order to do this problem. And so the friction force is going to equal this normal times the coefficient, either static or kinetic friction, depending on, in this case, we'll be using the coefficient of static friction. So the total F net, pulling this down the hill, is going to be equal to the friction force plus the parallel force. In other words, for this to slide down, the two forces that have to be overcome are the parallel and the friction force. So in order to calculate that stopping, whatever the deceleration is, you have to stop both friction and the parallel force dragging it down the hill. And so this is going to equal the friction force we already have, cosine of the, and then this is going to equal the weight times the sine of the angle. Now if we put all kinds of numbers in here, and first of all it talks about three different situations, one of which is the coefficient of static friction is 1 times the weight. Now, actually, something I need to do here before I put numbers in. Because as I was thinking about this problem initially, I was thinking they didn't give the mass of the car. Well, here's why they didn't give the mass of the car. If you take MA, mu s, and the weight is mg cosine theta plus mg sine theta, and notice that m is in all three parts of the equation. So you can cancel, divide through by m, so you don't need the weight. And so you end up with the coefficient of static friction times g cosine theta plus g sine theta. Now you can put the numbers in. You have 0, in the first instance, you have 1 times 9.8 cosine 6 degrees plus 9.8 sine 6 degrees. And if you do the math here, the deceleration is maximum deceleration is 10.8 meters per second squared. And then the next two parts are very straightforward. All you do is substitute different coefficients of static friction. In the second case, it's 0.7 times 9.8 cosine 6 degrees plus 9.8 sine 6 degrees. In that case, it turns out to be 7.8 meters per second squared. And in the third case, you have 0.1 times 9.8 cosine 6 degrees and 9.8 sine 6 degrees. And you add that together and you get 2.0 meters per second squared. So the key here is to see that if you put what weight is, you can cancel masses out. And that's sort of the trick of this problem. The foundation is that when you're calculating deceleration, you have to overcome two things, the parallel force and the friction force. Okay, the next problem is problem number, whoops, I skipped one. Problem number 7. Sorry about that. Problem number 7 says we have a situation where we have a mass of 65. Let me try that again. 65.0 kilograms. And there are two forces. Oh, this is the skater with two people pushing on this skater. And the skater's mass is 65.0 kilograms. And the one force is 26.4 newtons. And the perpendicular force is 18.6 newtons. And so you have one force this way and one force this way, and the skater's going to head off like that. And the first question is to calculate the total force, or the magnitude and direction of this resultant force. And this magnitude is going to equal the sum of the squares of these two forces, because you end up with a triangle that looks something like this, where one side is F1 and one side is F2, and this is the hypotenuse. And so you end up with this. And if you do the calculation here, you get 32.3 newtons. Now the angle here, the tangent of the angle is going to equal the side opposite, which in this case is, I'm sorry, I've got these labeled wrong. This is F2 and this is F1. It's going to be F2 over F1. And so the angle itself is going to be the inverse tangent of F2 over F1, which is 18.6 over 26.4. Sometimes the inverse tangent is called the arctangent. And so if you do that calculation, you get 35.2 degrees. So the total here is a magnitude of 32.3 newtons and a direction of 35.2 degrees, say north of the horizon or above the horizon. The second part of the problem asks what her acceleration is to get her started. And to make a long story short, what you have is the net force is going to equal the force that's exerted on her, so F tote, minus friction. But if you calculate, we've got this magnitude for this. If you calculate this friction force, that's going to be 0.4 times her mass, 65.0 times gravity. When you do that calculation, you get a number that is significantly larger than this total. And since the friction is larger than the total, then she doesn't move. And so the acceleration is equal to 0. If you can go ahead and do the multiplication there to find that. Now, C says, let's say if she's moving, what would her acceleration be? And that changes the friction force pretty dramatically. And so F net here is going to equal the same thing here, but this is going to equal ma. So if we're solving this equation for A, we end up with 32.3 minus, now the friction force this time, the coefficient of friction instead of 0.4 is 0.02 if she's moving, times 65.0 times 9.8, and all of this is going to be divided by her mass. And if you do this, this number is smaller than this number, so she does move, and her acceleration ends up being 0.30 meters per second squared. And the big difference here is the difference between dynamic or kinetic friction and the coefficient of static friction. The next problem Problem number 21, we're now moving from friction problems to drag problems. And remember the equation for drag is 1/2 times the coefficient of drag times the density of the medium times the cross-sectional area times v squared, velocity squared. In the first problem, we have a mass of 60.0 kilograms. Well, we have two guys. One guy has a mass of 60.0 kilograms, and the other guy has a mass of 90.0 kilograms. And it says that they are parachuting from a height of 5,000 meters in the pike position. Now, what that means is that it's feet down. When you look in the table to look up the coefficient of static or coefficient of drag, you want to use the number that's under a parachute with feet down. And the terminal velocity is the velocity when the drag is equal to the F net. Now what that means is that the person will accelerate until they reach a certain point where the drag is equal to the net force. And that means that the overall is equal to 0, okay? And so that means they're no longer accelerating. Terminal velocity is the velocity they reach where they quit accelerating. And so that means that FD for both of these guys is equal to their weight. And if you take that, so that means that mg is going to equal 1/2 c rho a v squared. And so the questions we start out with is what is the terminal velocity for each of these guys? And so if we solve this equation right here for v, the terminal velocity is going to equal the square root of 2 mg over c rho a. Okay? 2 mg over c rho a. And so for the first guy, the 60 kilogram guy, Vt is going to equal square root of 2 times 60 times 9.8 divided by C, and if you look this up in the table, it's 0.7, and it gives you the cross-sectional area. Oh, wait a minute, the density of air is 1.21 times 10 to the third kilograms per meter cubed, and then his cross-sectional area, again, is in the table, is 0.14. Also, it gives you these numbers in problem number 20 if you need them. And if you do the numbers here, you get 99.6 meters per second. So at his mass, his terminal velocity is 99.6. For the second guy, it's the same calculation. You just put 90 in instead of 60. Everything else is exactly the same. 1.21 times 10 to the third and 0.14. And if you do this calculation, you get 122 meters per second, excuse me. Now, by the way, these are ferociously fast speeds, which means when they hit the ground, there's not going to be much left, except for a few teeth that are probably broken in pieces. In order to calculate the time it takes for them to hit the ground, and it says to neglect the time to go from 0 to their terminal velocity, you would use the equation D is equal to terminal velocity times the time. So the time is going to equal the distance divided by the terminal velocity. So in this guy's case, T is going to equal 5,000 divided by 99.6. So his time is approximately 60 seconds. It's actually 60.2 seconds. And the second guy's time is going to be 5,000 divided by 122, and his time is going to be 49.2 seconds. Now, and what this shows is the reason why that, Galileo said everything falls at the same velocity, but that has to be in a vacuum. In a situation like this where you have drag, it does not fall at the same velocity. And that's why when you do things in real life, it looks like things do not fall at the same velocity. Galileo's situation was such that he had to be talking about a time where there is no drag. Okay, the next problem, problem number 23, again looks at a situation where the acceleration is 0. So that means that F net has to equal the drag plus the friction, the coefficient of kinetic friction. In this situation, the cross-sectional area is 0.7, and the coefficient of drag for the first vehicle is 0.28. And the two velocities are 70 kilometers per hour and 90 kilometers per hour. And I converted both of these to meters per second because you need to do that. This one's 14.4 meters per second. And this is 100 kilometers per hour. And this is 27.8 meters per second. So the Toyota, the drag force on the Toyota at 70 kilometers per hour is going to equal 1/2 times 0.28 was given as the coefficient of drag times the same density for air, 1.21 times 10 to the third, times the cross-sectional area, which was given at 0.7, times the velocity squared, which is 19.4 meters per second squared. And if you do all this calculation, the coefficient of drag is going to equal 44.6 newtons. The second one is the same calculation, just put 27.8 in here and you should get 91.6 newtons. For the Humvee, the calculations are all the same, except now it's going to be 1/2 instead of 0.28, it's 0.64. The Humvee has a much worse profile. The density of air doesn't change, but now you have a significant difference in cross-sectional area, and the velocities, again, for the two calculations are the same. And if you do these two calculations, you get, in one case, 356 newtons, in another case, 730 newtons.